So good afternoon to everyone. First of all, thank you for inviting me to be here. My name is Sara Jimenez Alfaro, and the topic I have chosen for this seminar is actually the topic of my research, that it is the study of fatigue life of wind turbines. So in the agenda, I will explain briefly my professional journey. Then I will describe why it's important to have wind energy and why it's also important to measure the fatigue life of these devices. I will give you some fracture mechanics methodologies that can be suitable to predict the fatigue life of wind turbines. And finally, I will finish talking about an important topic in this research, that is the numerical prediction of the effect of surface roughness in the high cycle fatigue. So first of all, I'm an MCA F4F fellow at Imperial College. I started 1 year ago in February 2024. F4F comes from Energy for Future. It is a network that is inside the Horizon 2020 MCA co-fund. In this program, projects are co-funded by Marie Curie Actions and also an entity, and in this case, the entity of our network is Iberdrola. Inside our network, we have projects related to energy, basically, but to different areas. For example, to energy storage, to photovoltaic energy, to smart grids, to electric vehicles, and finally to wind energy, where my research is allocated. We are a quite huge network. We are 28 fellows, 11 universities, and 3 research centers. And here I have included all the institutions that are taking part in the network, highlighting Imperial, my institution, and also MIT, Carlos III in Madrid. So we are a huge network, in my opinion. I also belong to 2 research groups. The first one is the Mechanics of Materials Lab at the University of Oxford. It's a research group in charge of studying the mechanical behavior of materials for different applications. For example, hydrogen, batteries, wind energy, concrete. Moreover, I also belong to another research group at University of Seville. It is a research group also in charge of studying the mechanical behavior of materials, but in this case to aircraft, solar energy, trains, wind energy, etc. And finally, I'm an alumni in the ITN new track. It was an ITM from Marie Curie Actions as well, where I did my PhD. I finished in October 2023. And these are the institutions that were related to me. Sorbonne University, where I did the PhD, University of Seville, where I also stayed for 6 months, and Safran Company, where I did an industrial collaboration, and I also stayed for 4 months. So now, coming back to the topic, I would like to explain you, before going deeper, why it's important to talk about wind energy. So today is Thursday, 20th of March, and from the beginning of the week, the world has consumed more than 4 million of terajoules. You can think that this is a huge quantity, but in fact, it is increasing. It's increasing at 2% per year. Sorry. 80% of this energy comes from fossil fuels, and about 5% comes from wind energy. Looking at these numbers, maybe you can think that this percentage is so tiny. Why it's important to talk about wind energy? Let me go further. 33 out of 195 countries have wind energy capacities, so not a big percentage in the world. And there are countries in which the wind energy represents a huge percentage in the world. For example, Denmark, it has 50%, UK 30%, and Spain 25%. So actually, wind energy is important, but it's particularly important for certain regions in the world where it's becoming an important energy source, such as Europe. No? In fact, when we talk about wind energy, we don't talk about these numbers. We talk about cumulative capacity, that it is the power that a certain installation or a wind turbine is able to produce. Just to give you a number, if we can produce 1 gigawatt of power, then we will be able to feed 1 million homes in the UK. So looking at the cumulative capacity in the last 14 years, you can see that it has increased dramatically. In the last 14 years, it has increased about 5 times. Moreover, I have also included 2 types of energy here. One is the onshore wind energy, that is the one generated on the land, and offshore wind energy, that is the one located in the sea. And as you can see, 14 years ago, offshore wind energy was representing just a tiny percentage because the technology was not fully developed. However, 14 years afterwards, it is almost the same between onshore and offshore. If you look at this number, the one in 2023, it is more or less 30 gigawatt. And in the UK, we have about 30 million homes. So that means that if we use the wind energy only to feed homes in the UK, we will be able to survive with that, no? To work only in the homes. So how is this wind energy being generated? Well, they are generated by wind turbines, and they are a clean and cheap system. They are one of the cheapest ways to get energy, and they are clean because they don't produce greenhouse gas emissions. Maybe you know that, but I would like just to clarify. They are made by a tower, a foundation that is connecting the wind turbine to the floor. The blades, normally the typical configuration is 3 blades. The nacelle that connects the blades to the generator to generate energy. The wind vane that is in charge of detecting the orientation of the wind so that the wind turbine is always facing the wind, the direction of the wind, and the transformer that is in charge of increasing the voltage of the energy so that it can be easily transported. If we talk about offshore, then the foundation is a little bit different because we are in the middle of the sea and we have different proposals. The most typical one is the monopile. We do it well to talk about offshore because, in fact, offshore has much more potential than onshore wind energy. This is because offshore wind turbines, they can be bigger because they are in the middle of the sea, so we can decide the size of these kind of devices, and they can face stronger winds. And in fact, this is very important for the UK because in the UK, we have long coastlines, we are an island, and we have strong winds. So we can use this methodology to get energy very easily. So offshore seems to be a promising solution, and in fact it is. It is the largest rotatory machine in the world. Here in this picture, I have compared the offshore wind turbine with the Airbus A380, that is the largest civil passengers aircraft in the world. And as you can see, it seems like a big animal next to the wind turbine. So the wind turbines, they are very huge. In fact, what is more interesting is that it's a technology that is growing really, really fast. The first wind farm was installed 35 years ago in 1991 in Denmark. It had 11 turbines and a total of 5 megawatt of energy production. However, nowadays we have projects that are huge. For example, I would like to highlight Hornsea, that is a huge wind farm in the UK. It has like 4 different phases, and now we are at the phase 2, Hornsea 2. And actually, it is the largest wind farm in the world. It has 165 turbines, and each turbine is able to generate 8 megawatt. The total production is about 1.4 gigawatt. But looking at those numbers, something very interesting is that one turbine from the Hornsea 2 is able to generate more power than the first wind farm that was installed just 35 years ago. So in 35 years, we have grown a lot. What's more important is that this growth is exponential. Nowadays, we have projects that are planning to increase this more and more. For example, the Dogger Bank is a project that is expected to be finished around 2026, and it will have a total power of 3.6 gigawatts. So since we are growing and we are growing really fast, we need to face many new challenges. One of these challenges that we need to face is that we need to face new winds acting on lighter blades. So in the last 40 years, the size of the wind turbine, it has increased 1 order of magnitude. And the blades, they have reduced their weight about 90%. So we have bigger wind turbines and lighter elements. And since we have bigger wind turbines, they are surpassing the atmospheric layer. So we are arriving to new layers where the boundary conditions are more complex, they are completely different, and we need to face that. We need to ensure that the blades will be working. We need to integrate this new system in the environment. And this is quite interesting because all the systems, they have disadvantages. The wind energy is not perfect. And these are some disadvantages. Once we install a wind farm, then we can affect to the wildlife, we can generate noise, we can affect to the crops in the case of the onshore wind energy. We can generate some vibrations in the floor. We can affect to radar interference, and even we can create new microclimates because the winds are facing, they are changing when they encounter the wind turbine, and the winds can change, so the climate can change. So many things that we need to face. Moreover, we want energy, we want clean energy, but we also want cheap energy. And this is very important in wind energy. So we are looking always for the lower levelized cost of energy. And this is completely related to the main topic of this seminar, that is the life cycle of wind turbines. Nowadays, the life cycle is between 20 and 25 years, which is really short. So in 25 years, we need to change the largest rotatory machine in the world, which is really expensive. And we need to look for different ways to improve this number and to increase this life cycle. Completely related to this fact, it is the idea of recycling the turbine parts, because after 25 years, we have many parts and we need to look for different ways of recycling them. If they are not damaged enough, then maybe we can reuse them in other wind farms. But if they are damaged, we need to look for another second life for them. And one idea that is proposed is to use it in different installations. For example, this Wicado playground in Rotterdam is made by old blades that after the service life, they were damaged enough to be in a wind farm, but they were not damaged enough to be playing with kids. So in the end, they have a second life. We need to prepare the wind energy to be the main global energy source. And this is something really important. So if you look at this map, I have highlighted here in the blue region the so-called exclusive economic zones. These are the zones where we can do something to get money from that, basically. And in red regions, we have the regions that now are occupied by wind farms. So as you can see, we have used a lot of space in this area, and we have limited space. We don't have infinite sea to put wind farms. We need to optimize this space. Moreover, not all the countries are like the UK. Not all the countries have sea, they have strong winds, so we need to face that. That means that if the country, for example, has low winds, we need to adapt the system so that it is able to capture the energy from these low winds. And the same situation if the country is used to have strong winds, then we need to look for new solutions to face that. And to all these challenges, we need to add the fact that we have political pressure, because there's now many challenges related to energy. And we all know, no? For example, the net zero target by 2050 in the UK that is proposing to arrive to zero greenhouse emissions by this year. And they have selected as well the wind energy as a promising solution to do so. So we need to face it. We need to face it really fast. And we have the political pressure to enhance this. So here we have many challenges for the researchers. I would like just to talk about one of these challenges, that is the life cycle of wind turbine structures. Why is it so short, just 20-25 years? Well, first of all, the wind turbines, they have to face a very complex loading profile. They have to face the wind that is acting on the wind turbine, the current, if we talk about offshore, the methodological phenomena, raining and any other kind of phenomena, the weight of the rotor, the nacelle, everything, the gyroscopic loads when it changes the orientation, and also the centripetal forces, because the blades are rotating and generating a centripetal force. So many loads. And what is more critical is that some of these loads, they are random. We don't know the amplitude and when they are going to happen. So we have some loading profile that is like this one. And during the life, 20-25 years, we can face about 1 million cycles. And what's worse, we don't know how it's going to be. This is critical, but it's also critical that the methodologies that are now being applied to estimate these fatigue lives, they are, in my opinion, too simple and too conservative. How are they doing this? So they select the material they want to apply in the structure. After that, they make the specimens, they go to the lab, and for each level of load, they applied what is called a fatigue test. They apply a cyclic load, they define the number of cycles at which the specimen is rocking, and they build these kind of curves that are called SN curves, where they relate the load with respect to the cycles. Now they apply a certain rule that is a Pan-Gremliner rule or another similar one, where they quantify the damage of the structure. This damage is just quantified by correlating the number of repetitions of loads that we have in a certain profile that we have estimated with respect to these values in the estimated in the lab. As you can imagine, this is not enough. We have many effects that in this methodology I didn't include. For example, we have the effect of wells because wind turbines, the towers, they are made in sections and they need to be connected one with each other. And to connect them, we need bolts and wells. We have circumferential wells and also longitudinal wells. So these wells, they are critical for fatigue as well. We have surface roughness that is very well known to be critical for fatigue because the different waves, they act as stress concentrators, as we will see later. And then we also have corrosion, that is a chemical reaction between the sea and the metal or the wind and the metal that is generating some pits, and the pits evolve until cracks are propagated. Moreover, these two, they are completely related because we want to put some painting to avoid the corrosion, but to put the painting, we need to generate surface roughness. So we have to decide which one is less worse, let's say. To add all of this in industry, nowadays, they apply a knockdown factor. That is an empirical value obtained doing many experiments, and they have come to the conclusion that this knockdown factor is around 3. So they take the curve we have seen in the specimen before, and now they apply this knockdown factor, they reduce the curve, and this is the curve of our fatigue wind turbine. In my opinion, this methodology is too conservative because we cannot include all these effects in just one value, and is making that the fatigue life is so short. It is between 20 and 25 years. So here is where fracture mechanics have a lot to say, because new fracture maybe they are able to predict in a better way all of these effects and to enhance the prediction of the fatigue life of wind turbines. Maybe the real fatigue life is 50 years, for example. So fracture mechanics is a discipline that is quite young. It started about 100 years ago, and before fracture mechanics, things they were breaking heavily. So we had the Industrial Revolution, we were building many things, many new machines, many new transport ways, and things were breaking and we didn't know why. No? So for example, I would like to highlight the Titanic because I'm sure you all know the accident. No? It happened in 1912. It was a dramatic accident because the boat was rocking in the middle of the North Atlantic Sea and about 1,500 people died. After that, an aeronautical engineer was motivating to create the first idea about how cracks can be propagated. It was in 1920, and he said that it was completely related to energy. So if the energy stored in the solid reaches a certain critical value, that he said that it was the critical energy release rate, then the crack will be propagated because the crack has enough energy to propagate. This was a brilliant idea, and in fact, it is still being used because this critical energy release rate is a material property that is now in the day-by-day of materials, but things were still breaking. For example, we have the Liberty ships that were American boats in the Second World War, and they built around 2,000 boats. Among 400 boats were damaged after their service, and about 150 boats were dramatically, catastrophically damaged. They were completely broken in the middle of the sea. So huge accidents. Moreover, we also have the Havilland Comets. I don't know if you know it, but this was the first passengers aircraft, and it started from here, from very close, the Heathrow Airport. And it was, in the moment, a very important news for the world, but some of these kind of aircraft, they were crashed, and they were normally crashed after about 3,000 hours of flight. And when they tried to see what was happening, they observed these kind of cracks that were generated around the windows. Why? Because there were stress concentrators, and these stress concentrators were generating fatigue cracks. So now we don't have stress concentrators in the wings, in the aircraft, in the windows. You can see that this is around, it has a round shape. No? So this was also pushing science to really understand what was happening. No? And Irwin in 1957 included the plastic effects in the theory given by Griffith. But although it was also a brilliant idea, it was not enough because all these theories, they were just predicting crack propagation. They were not predicting how cracks are nucleated in a material. So nowadays, in the last 20 years, this is the main effort of our community to study how cracks are both propagating and nucleated in different environments, combining it with a lot of multiphysics problems. Although we have improved a lot, things are still breaking, as you can see here. Wind turbines, for example, they suffer accidents because they have to withstand many loading profile, and we need to be prepared for that. They can be dramatically broken. They can be affected by corrosion, as you can see in the last image. So we need to do something. And I would like to present you two different theories that maybe they are suitable for this kind of predictions. One of these ones is the Caplet criterion. It is a criterion developed by Le Guillon in 2002, and it is able to predict both crack nucleation and crack propagation. It is based on two different conditions. So first of all, we assume a expected crack path in the solid. So we select a certain crack path, and over this crack path, we measure the stress condition, where we compare the tensile stress with respect to a critical value that is the tensile strength. Then we add the energy condition that is based on the assumption of a certain crack that has like a size delta L. It is called the newly created crack length. And for this delta L, we measure the difference in potential energy, and we divided it by this delta L, by this newly created crack length. And we compare this value with respect to the material property that was created by Griffith, the guy I've said you before. It was the critical energy release rate. So when both conditions are fulfilled, at the minimum admissible load at which it is fulfilled, we will have crack nucleation. And as a consequence of the application of this criterion, we will have a new crack nucleation length that is proportional to the material properties, as you can see here. This crack nucleation length represents a first jump that the crack does when it is nucleated. So this theory has been applied in many fields and applications. For example, we have used this theory to predict the fracture toughness of ceramic materials in bending test of microcantilever beams. We have also used this to predict either crack jam, crack propagation, crack deviation of some brittle matrices with short reinforcements, such as platelets or short fibers. And in fact, we have also included the effect of volume fraction and residual stresses. This was very interesting work because this was an industrial collaboration with Safran. Safran is also very motivated to improve their engines because they need to arrive to the net zero gas emissions that we were talking before. So they are trying to investigate new materials. And among others, one of these materials for their engines was very similar to this one. So we estimated for them the fracture toughness of their material for their new design. Although this methodology is very accurate and it has a low computational cost, it has a clear disadvantage. That is that we maybe don't know the crack path a priori, and we must know it in order to apply it. So for this reason, I would like to present you another different theory that is called the phase field for brittle fracture. And to understand this phase field idea, I would like you to imagine a bar in tension. Imagine that the bar is under a certain loading, and at a certain moment, the bar is broken into two different pieces. Then a sharp crack will appear. The main idea of the phase field is to substitute this sharp crack by a smooth region. And we will do it introducing a new variable that is called the phase field length scale that goes from 0 to 1. So it will be 0 if the material point is not damaged, and it will be 1 if we have arrived to the crack, if the material point is completely damaged. And with this, we can substitute this draw by this problem, where you can see that the crack is represented as a region, not exactly as a sharp interface. How can we do this with mathematics? Well, we can define a regularized functional that is defined as two different terms, the sum of two different terms. One is the internal energy, and the other one is the external work acting on the solid that comes from the volume forces and also the contour forces. So the solution that is in this problem, this phase field variable that is defining the damage and the displacement field is just the solution of the application of three different conditions. The first one is the irreversibility condition. It means that the damage cannot go back. No? If something is broken, we cannot fix it. The stability condition, the solution must be always stable, and the application of the law of conservation of energy. Applying these three conditions to this regularized functional, we obtain the solution of our problem. The elastic energy in the solid is defined as the sum of two different terms. One is the elastic internal energy density, that indeed it is the sum of another two different terms. You can see here, where you can see that these terms, they have a positive sign or a negative sign. This comes because we need to take into account the fact that only tensile strength are generating cracks. So if I do this, then the crack will be propagated or nucleated, but if I apply compression, we close the crack. So this must be taken into account somehow. And this is taken into account splitting the energy terms. And another term that is called the fracture energy density. So looking at this definition, this is the definition for the fracture energy density, you can see that depends on different terms. One of these terms is GC, the parameter given by Griffith, the first researcher that I told you that was investigating that. The other parameters, they can be estimated applying a one-dimensional case. So one-dimensional case is very interesting because we can get the analytical solution of this problem. No? So we represent the tensile stress with respect to the tensile strain. And you can see that we assume that when the tensile stress is arriving to a certain critical value, that is called the tensile strength, then catastrophic damage will happen, no? The crack will arrive. With this, we can define the parameters. You can see that L, the phase field length scale, the so-called phase field length scale, is also a property of the material. It depends on GC, on sigma C. CW is a constant. And finally, the function W phi, it can be different if we consider that, first of all, in the first part of this graphic, there is an elastic threshold, so no damage. This would be phi. Or phi squared if we consider that from the beginning the damage is growing, although it's not important enough to propagate or to generate the crack. So now we can also extend this to fatigue, that is the main topic, just adding a degradation function that is degrading the critical energy release rate, the material property that is defining fracture basically, over the cycles. Using this function just here in the formulation, we can apply cyclic loads. And this function, there has been many proposals for the definition, but I will tell you just one proposal that seems to be very suitable. Is a function of different terms here. A and B, they are the coefficients of the Baskin's law. This Baskin law is the equation that is defining the SN curve for fatigue that we were talking before. This curve that was relating the load with respect to the number of cycle to failures. Then R is the stress ratio. It's just the quotient between the maximum stress in the cycle and the minimum stress in the cycle. And finally, sigma E is what they call the endurance limit. It means the fatigue strength, the fatigue load, for which we will arrive to 1 million cycles. This parameter is really important, and please take it in mind because we will use it later. So with all of this, we are able to, or we are in conditions to apply this to one of the main topics of this problem, that is the effect of surface roughness. As I've said to you, this is very well known to be critical for fatigue. And now I would like to present you a numerical prediction we have made of the effect of surface roughness in the high cycle fatigue. So surface finish was always very well known to be affecting fatigue. And in the 60s, Marine introduced a correction factor that was a coefficient that was measuring the effect of the surface roughness in fatigue. This coefficient is just the quotient between the endurance limit, the parameter I've mentioned to you in the previous slide, of the rough specimen divided by the endurance limit of the polished specimen. So there were many attempts in the literature to measure this KS, this surface factor. On the one hand, we had experimental attempts. For example, in the 70s, they plot these kind of curves where they represented the surface factor as a function of the tensile strength for different values of the surface roughness. They were increasing the level of surface roughness, and they were measuring this using a lot of experiments. Or for example, in 2012, they also compute the surface factor as a function of the tensile strength, but for different surface finishes in the metal, in this case for steel. For example, as forged or hot rolled or machined, and they were relating more the type of production, the type of manufacturing with the surface roughness and the effect in fatigue. The problem of experiments is that they are expensive and they are also limited. To do a fatigue curve in this kind of area, we need about 10, 12 specimens. This is at least what regulations say. If we need to include the effect of surface roughness, then maybe we need more because surface roughness is random, is a random phenomenon. So we need to try several times in order to get a good value, a reliable value. So we need to spend a lot of money buying specimens and breaking them to build just one curve. Moreover, it's limited because although we have all the money we want and we can do any experiment we want, is limited because we cannot reach the infinite number of cases that we can have. So at some point, we need to stop, no, and just give a prediction. Moreover, that's why they started doing semi-analytical approaches. So the typical waves of surface roughness, they can be approached by notches. And these notches, they have been very well studied by our community. So they try to apply analytical approaches to predict the stress concentrator factor, how the stress was growing in the vicinity of the notch. They did it in static, and now to go back to fatigue, what they did is to apply some kind of empirical coefficients. So in the end, we had the same problem because, okay, in static we are good, we have a completely analytical solution, but when we go for fatigue, we need to do experiments to get these empirical coefficients and in the end to get the solution. So it was also very limited. That's why there were also numerical approaches, and most of these numerical approaches, they were based on going to the lab, do some surface roughness in the specimen, then use any kind of technique, for example, the scanning electron microscopy to measure this surface roughness, and then they import the surface roughness in the numerical, in the computer to do the mesh. Once they have the mesh, they apply any kind of methodology to get fracture. One of the problems of doing so is that we again need a lab to do it because we need to do the specimens, then we need to go for a very good measurement technology to get the microstructure, and finally we need to come back to the computer to do it, which is a long process because we need to touch everything, no? So in this context, the main objective of our work is to develop a numerical framework able to describe the effect of surface roughness, and in particular in the high cycle fatigue regime, because this is where the surface roughness is more critical, and this is what the literature is looking for, the effect between the endurance limit and in the rough specimen and in the polished specimen. So basically, our numerical tool combines two different tools. One is the phase field model for fatigue fracture that I have presented you before in the previous methodologies we were talking about. And the other one is the stochastic tool to build a roughness resolving mesh. So the idea is to build a tool that is able to generate the roughness without any microstructure from the lab. Basically, we want to answer to the question how much fatigue life is reduced for a given surface roughness and material properties. That's the question we want to solve. So I have presented to you the phase field for fatigue factor. I assume you know it. So we will go on with the second tool that is combining this general computational framework. That is how to build a tool for roughness, how to build a roughness without any specimen or any microstructure. So first of all, imagine that we have a one-dimensional case where this is a polished specimen and the points, the nodes of the mesh, they are represented by T. T is the initial position of the nodes in a polished mesh. And then at a certain moment, we want to apply a surface roughness. So we just apply a certain height deviation. How can we do it? We define the height deviation as the multiplication of three terms. RQ, that is the root mean square surface roughness. It is a typical measurement in the surface topology of a certain profile. L, that is the Cholesky decomposition of a matrix that is called R. R depends on T, the initial position of the nodes, and the correlation length, that we will talk about it later. And then W, that would be the Gaussian white noise. So including W in the formulation, we include the randomness of the problem. No, we know that surface roughness is random. Each time we can have any kind of profile, and with this we change the height deviation. So imagine we take two different Gaussian white noise, we will obtain two different height deviations profile. I told you about the correlation length, and this parameter is defined as a certain threshold of the ACF, the autocorrelation function. This ICF is a function of tau. Tau is just a parameter that we use to define this threshold that we are interested in. And now when we represent it, then we have different criteria proposed in the literature to measure the correlation length. The first one is when we consider that the ACF has decreased at 10%. The second one is when we consider that the ACF arrives to a value that is equal to 1 divided by E, is the Napier constant. And then finally, the third one, that is when we consider that ACF reaches a value of 0.2. So we have three criteria, and one of the objectives of our tool is, in fact, to reach to the conclusion which one is better, not to detect which one is better for the predictions. Sorry. So now the surface of roughness, as I've said to you, is a random problem, no? So we cannot just do a simulation and get the result. With that, we have nothing. We need to get reliable results, and to do so, we need to get a sample. So one of the problems is that we need to have a sample size. Another problem is that we have applied a Gaussian white noise, so we know that the surface profile will follow a Gaussian distribution, but we are not sure about the results. So to ensure that our results, they are Gaussian, they follow a Gaussian distribution, we take a sample that has a minimum of 30 specimens, and following the central limit theorem, then we will have a Gaussian distribution. So now we just have to check that our results, they are reliable. And we have established a criterion that is that we measure the relative margin error that is just made by the deviation, the typical deviation of our distribution divided by the expected value and also the size of the sample. And then we do it in a percentage, we compare it, and we say that our results, they will be reliable if it has a relative margin error of less than 5%. So now with that, for a certain cyclic load profile, we will compute our computational framework so that we get the numbers of cycles. I will explain you how. First of all, we build the mesh assuming that we have a polished specimen. So for the moment, we don't have any surface roughness. We just have the specimen we are interested in. After that, we define a certain characteristic for the surface roughness we want to know, no? For example, the average surface roughness, just typical measurements in a surface profile, or the correlation length, again the same, typical measurements that can be obtained in an easy way. Then after that, we obtain the matrix R, that was this original matrix that depends only on the correlation length and the initial position of the nodes. And after that, we start an iterative procedure. So for a certain level of load, we compute a new Gaussian white noise, so one proposal for this randomness. We obtain the height deviation profile, we build the rough specimen with our tool, and finally we use the phase field model for fatigue factor to obtain the number of cycles to failure. We repeat this until we have a minimum of 30 specimens, and also our relative margin error is lower of 5%. Once we have that, the estimation or our estimation of the number of cycle to failures will be just the mean of this distribution, and then we have the value. So now let's go for the results. Let's see if this is working or not. We have proposed a model here that is inspired in some experiments that were done by Sain et al. In 2019. And this model is also made of a material that was the one they used just to compare with the experimental results, that is IC4130. You can see here the material properties, where you can see that GC is just, or the ultimate strength, they are just material properties that are given in the day-by-day for materials. And first of all, we need to define the parameters of our model. As I've shown you before, when we were presenting the phase field model, we have different parameters, so we need to define them and to be sure that this works. No? So we use just the polish specimen with no roughness at this stage, and we compute our parameters. We use the phase field to check that our numerical fitting is fitting the experimental one. So we approach just the experimental results of the polish specimen. Once we have our numerical calculations completely calibrated, then we go on with the surface roughness. So first of all, we have changed the average surface roughness, and assuming that we don't know the correlation length, that maybe is the most complex parameter that we can find, and sometimes they don't give it because they don't give the surface profile, or they just don't give it because they didn't think that it was interesting, then we have measured the surface factor. Since we are just considering that we know one of the two parameters that we need, we have for each value a certain range of possibilities. No? And then we have also highlighted here in bars the stochastic of the distribution. What's more, at this stage, I would like just to make a point. That is that now I'm talking about the average surface roughness. But when I presented this tool, we were talking about the root mean square surface roughness. That was RQ, another parameter. Well, indeed, in this case, it doesn't matter because we are following a Gaussian distribution, and that means that these two typical measurements in surface profiles, they are related. So we can use one or the other one. So first of all, as you observe, when we increase the average surface roughness, the ranges are bigger. This is because the presence of the correlation length and also the stochastic is also more important. Here in black, we have represented several experimental data. We have represented the estimated given by Johnson in the 70s, that this was this first graphic I have shown to you in the introduction, and also the experiments done by Sain et al. In 2019. And as you can see, the experiments fall into the ranges. Moreover, as soon as the average surface roughness is growing, the experiment seems to be closer to the upper bound. So that means that the typical correlation length of those profiles maybe is bigger. With this, we have an approximation, but imagine if we know the correlation length. This is what we are going to do now. Here in this table, we also have the experiments of Sain et al., but in this case, they gave to us the surface profile, this kind of graph that is very typical in the papers for surface roughness. And with this, we have just extracted the data, we have computed the ACF, and using the three criteria, we have got the correlation length. So once we have the three different correlation lengths, because we have three different possibilities, we have computed our numerical result, our numerical surface factor, and we have compared it to the experimental one. As you can see, results are very accurate. In fact, the most accurate one is the ACF equal to 0.2, because the prediction, it has a less than or around 1% error, so almost the same value. This is not just a random thing. The ACF equal to 0.2 is the criterion proposed by the ASTM regulations. So that means that they were right. This is the most accurate one. We have checked that. Each time I change the parameters, something changed in the computer. This is what I want to show you now. So each time we change it, we change the mesh. Here I have included some different meshes for different cases. I would like to show you just the most critical ones. This is a case for a very low value of the surface roughness and also a very low value or an average low value of the correlation length. You can see that the specimen is almost flat. It's almost a polished specimen. There's almost no surface roughness. However, if we go for extreme value, for example, the average surface roughness with a very low correlation length, then we can see huge peaks, as you can see here. So one of the critical points is how to define the mesh in a way that is accurate. Because if we have those peaks, we need to establish the mesh size around these peaks, no? So we have established a rule because we have another problem that is in the phase field model, we also have a requirement for the mesh size. And we have established a compromise relationship where the mesh size, 5 elements, need to define either the correlation length or the phase field length scale, just a minimum of 2. And with this, we ensure that the data is correct. How do we know that 5 elements? Well, it is not our idea, in fact. It was proved in the literature for the 2 cases. So we just follow, in this case, their tests. After that, we have included here just the damage profile, just to show you how it works. So these peaks are acting as stress concentrators, and in those peaks we have very big stress so that the crack is nucleated. Once the crack is nucleated, that is represented in red color, then it is propagated until it arrives to the center of the specimen, more or less. Since we are in a force control problem, at a certain moment, the damage variable will cover a huge region, because in force problem, it's like the force goes, stops at a certain value, and the displacement can be infinite in the results of the force displacement curve. So here is translated in a huge region where damage is equal to 1. At this point, we define our fatigue failure, and we say that we have arrived to the number of cycles we are interested in. Now, I would like to show you a comparison with key parameters. To define this, I have defined a range, and to define the range, we have based our values on the previous range defined by Johnson in the 70s. This is a very well-known experimental campaign, that's why I use it, but we have made some changes. First of all, if the roughness was less than 0.2, we have removed it, because according to the regulations, its effect in fatigue is almost negligible. Moreover, we have changed these 2 values just for the economy in the simulations, because we wanted to compare with experiments of Sain et al. So we just changed these 2 values. And we have also included additional values to really capture the evolution of the surface factor with respect to these 2 parameters. We can do it. This is an advantage of our computational tool, that we don't expend a lot of money. We just use a calculation cluster, so we can include as many parameters and as many values as we want. And finally, we have decided the range for the correlation length based on a proposal in the literature. So now we have built this kind of operational maps. You can see here that we represent the surface factor as a function of the average surface roughness with respect to the correlation length. For very low values of the correlation length and very high values of the surface roughness, we get a surface factor that is around 0.5. That is really critical. Imagine a polished specimen with a certain load has 1 million cycles. It's broken at 1 million cycles. But if we include this surface roughness, it will be broken with the half. It means with 500,000 cycles, just the half. Is very critical. And since we are with a random distribution, I have also represented an operational map for the margin error, the relative margin error. As you can see here, it is bigger for bigger values of the average surface roughness and the correlation length. But looking at these numbers is always less than 5%. This is something we have done it artificially. We have forced that we have repeated the simulation until we arrive a maximum of 5%. So now we have also done the projections of this surface factor with respect to the 2 parameters. First of all, you can see that there's not a smooth evolution of this. This is because we have random distributions. So you can see here the different margin errors that we have for each point, and this is why we have those peaks. And moreover, the influence of the surface roughness becomes negligible for very low values of the, the influence in the surface factor becomes negligible for very low values of the average surface roughness, as you can see here, because it's like a straight line. We have also represented the evolution of the surface factor in a sample. Here you can see the margin error for different simulations. As soon as we increase the number of simulations, the margin error is being reduced. Moreover, we can see that for bigger values of the average surface roughness, this margin error is much bigger. It changes a lot. Looking at the number of cycles that we can predict, it can be even dangerous because here we have selected a load level just to have an expected value of around 2,000, 3,000 cycles. And you can see that for very big values of the average surface roughness, in one case we can have 2,000 cycles, in the next one we can have 10,000 cycles. So we don't know. This is the key point of randomness. So just to finish, I would like to give you some concluding remarks. First of all, we have developed a computational framework that is able to predict the effect of rough surfaces in fatigue life of any kind of specimens. We have shown you that there is a good agreement, both qualitative and quantitative, with experimental data. We have built some operational maps where we have faced the surface versus the fatigue effect. And this is good because we can propose these operational maps as design tools so that people can design their specimens or their materials in order or following these operational maps. And what's interesting is that the model is including the effect of randomness, that is a natural effect in the surface roughness inside the model. And we are obtaining, although we have this, we are obtaining reliable results. And finally, we have not included this because we didn't have time, but we have also done estimates for 3D printing for additive manufacturing and pitting corrosion. And we have checked that we are able to give good estimations of the surface factor in different environments, checking with experimental data. So thank you for your attention. And of course, if you have any questions.
Do you have any questions?
Yeah. So when we try to estimate the fatigue life, generally the fatigue life consists of three parts. One is the life till initiation of crack.
Yes.
And the propagation time, like the life when the crack propagates to final failure. So, and the surface, any surface roughness can lead to a increase in K value stiffness near the surface. So how do you account for the crack propagation when you consider the material as a bulk?
Well, in this case, it's a little bit tricky that because we have accounted the crack propagation effect because we are in a force control test. So for us, the failure is not when the crack is nucleated, it's when the complete specimen is broken. So we include the crack propagation as well. But we have not computed the difference between crack nucleation and propagation. That would be very interesting as well. I don't know if this was your question. But...
Yeah, because the stiffness value keeps on changing at the surface. So how do you account for that?
Sorry,
because of the strain hardening, the stiffness value keeps on changing continuously.
Okay, yes, but for the moment we are not including this strain hardening because we are in the high cycle fatigue. So one of the points is that we don't include any plastic effects, assuming that it's only high cycle fatigue or retail materials. But indeed, it's a good opinion because we are working on that. We are working on plasticity, so I will take into account this. Thank you.
Thanks. Do you have an estimate for the effect of your work life? You said it's 20 to 25 years at the moment, and
yes,
you've done a lot of work. So
it's a really good question. Well, for the moment, we didn't try it in real structures. It's just an initial work of the project, but we want to do it. In fact, this is like the collaboration we have with Iberdrola. The idea is that more or less in several months, I will go there. They will give me real data and I will try to join everything together. That's
So what type of increase would be a good result from your opinion?
good. I mean, I'm very optimistic, but I think it can be even the double, because for me, like, these 3 is too conservative. So maybe it's 50 years. I don't know if aircraft, they can fly during 50 years. Why not these kind of machines?
Of course, yes.
That's my idea, but maybe I'm too optimistic. Eh?
Thanks.
So one more thing,
Yes.
we tried to see what is the mean stress in a life cycle, basically a sine curve. Also, the amplitude ratio also matters, right?
It matters. It is affecting. For the moment, we have considered only r equal to -1. So that means that is positive, negative, the same value. But actually, if you change it, of course, you will change the results.
So in a real life situation, the
It's changing a lot. Yeah, we will need to study the whole profile to apply it. But the idea is to give this as a design tool. And then once you have the tool, you can do whatever. So you can apply this in different situations. That would be the perfect idea.
also, I think in the equation I saw only the mean stress is being taken into account, not the alternating component.
No. In the end, is being taken into account, the alternating, but yeah, in the model we take it, but we don't model the cycle, because in the phase field, in this formulation, the stress ratio is just considered when we define the degradation function. So we just apply for each iteration, we apply the load, we give this stress ratio, and then the formulation is able to capture the effect of the stress ratio with that.
And also one more thing.
Yes, of course.
Since you maintain the boundary conditions as force, so when we take a very high variation in stress,
Yes.
whether the low cycle fatigue cases be included, or only is it applicable for a high cycle fatigue?
Only for the moment for high cycle fatigue. I mean, you can apply it for low cycle, but since you don't have plasticity, then the results for metals, it will not be reliable for sure. That's my present work, in fact. For retail materials, yes. But for metals, if you can have it, you can compute and you can get a result. But it just reproduces the basket law, not the Coffin-Mason law, where you have this change in the slope. Yeah, it has limitations, of course, but I hope with the plasticity, these two works together, it will be the perfect solution.
So just following on from what he said, that the wind, like on a wind turbine, it would experience a spectrum load, and the outputs, you have a number of cycles for constant amplitude loading. So with that, is the idea then that you'd use it in conjunction with something like Miner's rule or some other kind of cumulative loading tool to then predict life for a spectrum load, or is that more?
We will introduce this in the model by this R, as I said to him. So the idea is each time we compute the phase field, we run the simulation, we can include any parameter we want. So if we have a different loading profile, then we, for one cycle, so for one iteration to the other, we change R, the stress ratio, and this will be taken into account.
Okay.
So yeah, the tool is able to compute the different loading profile. But for the moment, we just use this, especially because we had the experimental data with the